we're going to look at a cyclic quadrilateral. What are they and what can they do for us? Well, a cyclic quadrilateral is the following. It is a four-sided figure which has every corner point on the circle. So something like this. Sometimes they're rectangles, sometimes they're squares, sometimes they're whatever. But they've got each corner point is on the circle. Now there is a very special law about cyclic quadrilaterals, and that is the opposite angles are supplementary, which means they add up to 180 degrees. So if you knew that this was 80 degrees, you would know that the angle across from it is 100 degrees. And so on. So that's the cyclic quadrilateral. And that's what it is. Now the way this law is written up is the following. I'll just write it in a kind of a two-way writing. A quadrilateral is cyclic if and only if, and I'll explain that in a moment, the opposite angles are supplementary. Now, this is a funny word, if and only if. What it really is saying is that we have two theorems built into one here. What it says is, if we wanted to define a quadrilateral to be cyclic, we have the following ways of doing it. A quadrilateral is cyclic, so that would be the given information. So it's kind of like saying you know you have a cyclic quadrilateral. Then as a consequence of that, okay, you know it's a cyclic quadrilateral, so therefore we know the opposite angles are supplementary. So that's one direction that this theorem works. Given this first part, therefore we know the opposite angles are supplementary. But it can also work in the other direction. If we're given that opposite angles are supplementary, we can conclude, therefore, this is a cyclic quadrilateral. So let me just show you an example of that, because that one probably seems a little bit strange right now. But what it's saying is this. If I presented you with a four-sided figure and said, is that a cyclic quadrilateral? You might say, well, I don't know. Maybe if we could draw a circle that goes through each of these 4 points. How do you know if you can? I mean, we could kind of trial and error and try something, but a very quick way is to use the previous theorem. If these opposite angles add up to 180, then we know it's a cyclic quadrilateral, and we know that there is a circle that goes through all of the 4 corners. So if this was 120 degrees, and it turns out this was 60 degrees, then that's enough to say, yes, we know this is a cyclic quadrilateral. So the theorem, when we say if and only if, what that really means is the same thing as this theorem can work in both directions. You can start with the one thing, conclude the other, or switch it around. It's kind of 2 theorems built into one. So now let's look at some examples of cyclic quadrilaterals in action. So I'm going to start off with perhaps a simpler one. We're going to have a nice cyclic quadrilateral that coincidentally has a couple of parallel lines. Now, these we would know are parallel because there's little arrows drawn. And we know it's a cyclic quadrilateral. So let's suppose, and my drawing here, I'm going to say this is 88 degrees. And now we're going to try and find angle 1 and angle 2. And theoretically we could find angle 3, but we'll just work with this. So, first things first. Well, this is a cyclic quadrilateral, therefore I could find angle 2 quite easily because these 2 angles have to add up to 180 degrees. So I'd go 180 minus 88, which means I need this angle over here to be 92 degrees. Okay? And in a similar way, when you have parallel lines and you have two interior angles on the same side of your transversal, which is what we have here. Just to sort of show you away from the circle what I'm talking about, we have two parallel lines. We have a transversal. This angle and this angle are also going to be supplementary. So coincidentally, angle 1 here also works out to be 92 degrees. And that's because of the parallel lines thing. So that's an example of cyclic quadrilateral in action. Let's look at another one that's a little bit more complicated. And I think I'm just going to turn the camera off. Okay, here's an example, and we're going to try and figure this missing angle here, angle x and angle y. And now we've got some tools to work with, the knowledge of these cyclic quadrilaterals. Well, let's see what we can figure out here. We can start off by saying, oh, that's 100 degrees, and we have a straight line. Angles on a straight line are supplementary, so we know this angle here must be 80 degrees. And then we notice, hey, this is a corner, this is a corner, this is a corner, and this is a corner. All four corners are on a circle. Therefore, this is a cyclic quadrilateral, which means angle x must be 100 degrees. It's got to be supplementary to the 80 degrees. Okay, now what about angle y? Well, here we have a very large triangle. That's 55 degrees, that's 80 degrees. In angle y, the three of them have to add up to 180. So all we have to do is go 180 minus 80 minus 55, and we'll get angle y must be 45 degrees. If we wanted to, we could now continue. We could figure out this angle here, because 45 degrees and this angle have to add up to 180, because we have the cyclic quadrilateral. But they didn't ask for it, so I'm not going to do it. So that's this example here. Okay, this example here, I'm looking for a couple of unknown angles, angle x and angle y, and we're told that this little chord and this little chord are equal in length, and that this angle here is 42 degrees. That's all we're given. So let's start filling in what we can. First thing I notice is that this guy here, this angle here, is subtended by the diameter. So that's 90 degrees. So that might be very helpful to us. The next thing that I can do is recognize that this chord is equal to this one, and they're subtending these two angles. So whatever x is, this is equal to it. And that's an observation that may be very useful to us. Okay, now I'm going to look at a kind of a bigger sort of step back from the picture and say, hey, I've got a cyclic quadrilateral with these four corner points. Okay, it's the outer line segments here. And what I can identify is I know this entire angle here because that's 90 plus 42. So this angle here must be supplementary to the both of these put together. So just ignore the line down the middle for now. This angle here is 90 and 42. Those two together is 132, and that's got to be supplementary to the two of these. So we go 180 minus 132 leaves us with 48. So together, these are 48 degrees, which means angle x, since these are both equal, angle x must be 48 divided by 2, or 24 degrees. Now I can just finish up by recognizing if this is 24 degrees in this little triangle here, I've got 24 degrees, I've got 42 degrees, and how much more to make 180? So we just grab the calculator and go 180 minus 24 minus 42, and whatever's left must be angle y. Turns out to be 114 degrees. Okay, and so that's that one wrapped up. Okay, I'm now working on what will be the last example for cyclic quadrilaterals. I've got this circle here, number of line segments on the go. This one's a diameter, and we're told this angle up here is 30 degrees. Now, what we're going to try and do is figure out the length from A to B, and then the length from B to C, and lastly we're going to try and figure out B and D, that line segment there. So let's just identify a few things before we get to work here. That's a radius, and that's a radius. Okay? So what does that tell me? If this is a radius and this is a radius, then I have an isosceles triangle, which means I know this angle here must be the same as that angle up there. So both of these are 30 degrees, which allows me to figure out this angle here. Because in a triangle they got to add up to 180. So 180 minus 30 leaves me with 120. Which means this angle here, since we're on a straight line, these angles are supplementary, and that's got to be 60 degrees. Well, now that's interesting because this is also a isosceles triangle, because that's a radius and that's a radius. So I can figure out these angles here. If we take the 180 degrees, take away 60, that leaves us with 120. 120 divided into two angles would mean that these are both 60. Now there are other ways to have figured out that these are all 60, but I'll leave that to you. Now we have an interesting thing to observe. This is no ordinary triangle. We know it's isosceles, but it's more than that. All three angles are 60 degrees, which means it's equilateral, which means all three sides are the same length. So if this one's 5, then I know this one's 5, and this one's 5. And since these are all radiuses here, I know they're all going to be 5, which means the first question of A to B is going to be 5 plus 5, so the diameter is 10. Now I'm looking for B to C. Well, there's a lot of clutter here, but what you actually have is a nice big right triangle. This angle 30 and 60 is 90 degrees. We know the hypotenuse of this triangle is 10. I'm just going to redraw it over here in miniature so you can sort of see what's going on. Okay, this is B, this is C, and this is A. We know that's 5, we know that's 10, and we're looking for, we'll call that x. Well, that's just going to be Pythagoras' theorem. So all we have to do is go hypotenuse squared equals this side squared plus this side squared. So we're just using good old Pythagoras here. So 100 equals 25 plus x squared. We take the 25 away. X squared is 75, so x is the square root of 75, which you can break down a little bit if you think of it as root 25 times root 3. So we can write that as 5 root 3. Okay? So now we've got what we call x, or BC, is 5 root 3. And now I'm ready to keep going and find DB. Make a little bit of room for that work. So what else can we conclude now? Well, in this triangle, here's what we have. First of all, this is also a right triangle. How do I know that this is 90 degrees? Because this angle is subtended by the diameter. So we've got a nice big right triangle here. So if we just draw a mini version of it, it looks something like this. We know that this length from B to A is 10. We know this side and this side are the same because they've got the double check marks, and we know this is a right angle. So what I'm going to do is I'm going to call this side here x, and I know that side is x. So if I use Pythagoras now, there's a little bit of algebra left to do, but not too bad. Hypotenuse squared must equal this side squared plus this side squared. So what I have is 100 equals 2x squared. We'll divide both sides by 2, x squared equals 50, and then square root the 50. So that length is the square root of 50, or if we break that down into lowest radical form, we'll go root 25 times root 2. Let's remove the clutter here. Root 25 is 5, and root 2. So there you have it. Geometry in action. We're going to stop.